We're ready to look at the back on that, so number 11. So we're still talking about being continuous. The front side we kind of did just by thinking about the function a little bit. The back side I want to look at the graphs, but let's just kind of summarize everything that we found yesterday. So we know can our graph be discontinuous? What are we looking for? Breaks on a piecewise function. And what was the other type of function? Yeah, so if you're looking at a graph, you're looking at an open circle or a break. In terms of the equation, that means we're looking at piecewise functions and rational functions. And we've talked about different types of discontinuities. So the different types we had were what? Removable, infinite, and jump. Okay, those are easy to identify when you're looking at a graph, but possibly a little bit harder when you're looking at the equation. So a removable is when you have something like this. When you have a fraction and something cancels, that is a removable discontinuity at x equals -3. So in a fraction, when something cancels, that makes it removable. The other situation where we have a removable is when we're looking at a piecewise function. And these conditions are an equal and a not equal. That usually means you're just going to create a hole in your graph. So that is a removable discontinuity at x equals 0. All right, when do we have an infinite discontinuity? Vertical asymptote. So if you have a fraction and it doesn't cancel, so this didn't cancel, so that means it's a vertical asymptote, so that is an infinite discontinuity at 1. Then the jump discontinuity. That's when we have a piecewise but our conditions, instead of equal and not equal, you have inequalities. Then that makes it a jump because you will physically jump from one piece to the next at that x value. So these are just some general guidelines to help us kind of identify what we're looking at and what kind of discontinuity we should expect. So if you guys look at that handout from yesterday, we have the 4 graphs left, so we're going to go ahead and draw those graphs. Remember, we're on the notes handout, so I think on that one, the last question was probably 14. So we have notes and handouts that look almost the same. We can probably predict, just by looking at that equation, can you tell me where we would have a discontinuity? -3. And what kind of discontinuity would it be? That should be a jump discontinuity. But the question is to look at the graph as well. And this is kind of good practice for us to remember how to graph these piecewise functions. So remember, we have to plug -3 in. So if you put it into the first one, the opposite of -3 squared. So -3 squared is 9, so that would be a -9. plus 12 minus 4 gives us what? And would that be open or closed? Open, because it didn't have an equal to. And then if I put in negative 4, so I'm just making my T chart here. So I put in negative 4, so we get a negative 16 plus 16 minus 4. That's negative 4. If we wanted to do another one, we could put in a negative 5, so we would have negative 25 plus 20 minus 4 is negative 9. So that piece is a part of a parabola. To graph the second one, we also start with 3, but this, or negative 3, but this time it would be closed, and then we need things larger. So if you put in negative 3, we get negative 5. It's closed. Put in negative 2, you get negative 3. Put in negative 1, we get negative 1. My graph is really kind of not perfect. Okay. So we get something like that. So would we agree where we write it first? So we have a discontinuity at negative 3, and we can see it is a jump. So I'm just trying to get you practice with the front side. We really just looked at the equation. The back side, we're looking at the graph to kind of confirm that. So number 12. We look at this one. Where do you think we'll have a discontinuity? At 3. What kind do you think it would be? Removable. Let's check. So if I graph the first piece, it says x cannot equal 3. So we have to put in some points. I'm still going to put in a 3, but when I put that in, it will be open. So if I put in 2, we get negative 1. 3 gives me negative 1.5. 4 gives me negative 2. You could always put in more points if you needed. So what we have here is a line with an open circle on it. And then the second piece says 2 when x equals 3. That's just a closed dot at the point 2, 3. Okay, so where we write? So discontinuity at 3, and the type is removable. Right, why don't you guys see if you can try the next couple, or at least the next one. I'll give you some time, get as far as you can. So we still have to put in the -1, it will be open. Because it's a quadratic, you might need more than 3 points, so put in whatever you need. If I put in -2, -2 squared is 4, 1, -1, 1, 0, 0, 1, 1, 2, 4. So -1, 1 is open. So we just have a parabola with a hole in it. And then the second one, 5 when x equals -1, so that is just a single point. So it is discontinuous at -1. What type of discontinuity? Removable. And we know that anytime we have piecewise with an equal and a not equal point, that is likely to occur. Is that one okay? Next one, so a little more tricky. Let's go ahead and factor. So the denominator, multiply -2 and add to +1. That would be x plus 2, x minus 1. What happens? The x plus 2 cancels, so I get -1 over x minus 1. So you should be able to tell me right now, where is this discontinuous? At 1 and -2. What kind of discontinuity is 1? Infinite, because we'll have vertical asymptote. If something cancels, what kind of discontinuity? Let's confirm it from the graph. So we know when we graph this, we can't plug in a 1, so that's a vertical asymptote. Okay, if I put in 0, I get 1. If I put in -1, I get 1/2. If I put in a 2, I get -1. If I put in a 3, we get -1/2. I mean, you could certainly use a calculator to kind of help confirm this. So we have, if you're looking at your calculator, it looks kind of like this. What your calculator will not show you, so if you just plug this in, you're going to see something like this. However, that's not completely accurate, because if you remember from college algebra, when something cancels, that puts a hole in the graph. So we know the x is -2. If you plug in -2 into what's left, we get -1 over -3, so +1/3. So -2 1/3 is actually an open circle on this graph. So then we can see the two types. We have an open circle here, so that's the removable at -2. We have a vertical asymptote here, so that's the infinite at 1. Any questions on this stuff? Let's go back to the notes handout for our packet that we were working on. All right. We know anytime we have absolute values, what do we have to do? Do the piecewise, rewrite it. What would be my breaking point here? What makes x minus 1 equal 0? 1. So we'll have one piece if x is bigger than 1, one piece if x is less than 1. Can x equal 1 on this problem? No, because why? Give us 0 on the bottom of the fraction. Okay. So if I look at this, if x is greater than 1, does the absolute value change anything? No, because it would be a positive. So you just get x minus 1 over x minus 1 cubed. So what happens? You can cancel one of the x minus 1, so it gives you 1 over x minus 1 squared. Okay, second one, if x is less than 1, then it's a negative inside the absolute value. So the absolute value does the opposite of that. X minus 1 still cancel, although this time we have a negative 1 over x minus 1 squared. Okay, this one is kind of breaking the rule that I told you. I told you most of the time on those piecewise, if you go from a greater than to a less than, it's usually a jump. But when you notice, I didn't include 1 in this. Because what's happening at 1 on both of those? Vertical asymptote, because it makes the bottom 0. So this is discontinuous at 1. But it is infinite. Because we can't plug a 1 into either piece. It's giving us a vertical asymptote. Next one, find A, which makes the function continuous. So if I want this to be continuous, that means what has to happen with those two pieces? When you graph them, they have to meet, right? What's the place where it could be discontinuous right now? At 1. So if it is continuous, when I plug 1 into both of these pieces, I should get the same thing. All right, so let's do that. If I plug a 1 into the first, has to equal the same thing as when I plug a 1 into the second. So we get that A has to equal 3. In order to make it continuous, the pieces have to match up at that breaking point. Any questions on that one? One last thing to talk about is the intermediate value theorem. This is something you had in Algebra 2. We did it in college algebra. And we always said we were dealing with polynomials when we looked at it. And we said, okay, if I can plug in a value for x, so if I put in something for x and it gives me a negative answer, and then I have another value for x, and when I plug that in I get a positive, the only way you can get from a negative to a positive is by hitting 0. Okay, so if I put in a 1 and I got a negative answer, and I put in a 3 and got a positive, then that meant somewhere between 1 and 3 my graph hit the x-axis. So we're still using that, but it requires something about the graph. The only way this works is if your function is continuous. Because now that we're talking about all these discontinuities, we know if it's not continuous, could it be a negative at 1 and a positive at 3 without hitting 0 in the middle? Absolutely. For all I know, I have a vertical asymptote in the middle. And so it never actually hit that value. So the intermediate value theorem only works when the function is continuous. So when we do these problems this year, we have an extra step. Last year, all you had to do was basically plug in two x values, and if you could get a positive answer and a negative answer, you could just say there's a 0 in between. Now we're going to have to state if the function is continuous or not. So if I'm looking at this one, show there is a root to the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0. So I want to prove that somewhere this does in fact equal 0. Okay, first thing, look at the equation. Is this continuous? Yes, you have to tell me that. I am not going to make you give me a big justification for why it's continuous. I trust that you know, but if you don't tell me it's continuous, you lose a point. Okay? Now, a lot of times on these, I might give you an interval. I might say, show there is a 0 between 1 and 5. And if I do that, that means you can plug a 1 in for x, plug a 5 in for x, and hopefully the sign changes. This time I didn't give you the interval, so that means we just have to find our own. So pick an x value. Let's try something. We put in a 0. You want to try that? So if x equals 0, we get out -2. So what I know on my graph so far is 0, -2 is point on the graph. It's continuous. So now all I need is a different x value that would give me a positive answer. What do you want to try? I don't think 1 wouldn't give me a positive, would it? Let's try 2 and see if that does. -32 minus 24 is 8 plus 6, just 14 minus 2 is 12. Okay, and then you just have to write something so I know you realize what happened here. So we found when x was 0, we got a negative answer. When x was 2, we got a positive. Since it's continuous, that means somewhere it had to cross the x-axis. So I'm going to say the sign changed. So a 0 exists between 1 and 2, or sorry, 0 and 2. So there is some x value between 0 and 2 that we could plug in and make this equation equal 0. Any questions on that? Last one of the day. Okay, assume f of 1 equals -5. So I have some function. When I put in 1, I'm getting out -5. And f of 3 equals +5. Does there have to be an x between 1 and 3 where the function equals 0? Why? Okay, say that louder. All right. If it's continuous, there is no way to get from a positive to a negative without hitting 0. But I never told you it was continuous. For all I know, the graph looks like this. And would you have ever crossed 0 in between? No. So the answer here is no. We don't know the graph is continuous. So intermediate value theorem only works for continuous functions. All right, you have that handout from yesterday that's due tomorrow, and you've got time to work.